We have a beam subjected to a moment of 40 kilonewton meters. We want to determine the bending stress at points A, B, and we'll also look at point C here, which I'll call just right below B there. So we get stress equals mc over I, standard equation for any stress due to a bending moment. So first step is almost always going to be find our moment of inertia. So if we draw a cross section, it looks like this. So you can split it up however you want. I'll go ahead and call this shape 1, and these are both shape 2, and we'll just multiply it by 2. We can do that because they're 80 squared. From there, and there, it's the same distance. So it works out. So we get moment of inertia equals shape 1 has a height of 0.15, or a base of 0.15, at a height of 0.05. I'm doing this in meters. You could do it in millimeters, but you'd have to convert later on. Easier if you just do everything in newtons and meters. And that's over 12. It's a rectangular cross-section. And then plus 2 times, because we have 2 of these shapes, they are 0.05 by 0.05 over 12 plus 80 squared. The area is going to be 0.05 squared because it's a square. And the distance from here to here is also going to be 50 millimeters, or 0.05. So we get our moment of inertia to be 15.1042 times 10 to the negative 6th meters to the 4th. And because we're in meters, and these are pretty small dimensions overall, it's going to be a tiny number. If those were big numbers, you could also end up with a really big number. That's normal. Don't worry about it. So we get stress equals, we'll do point A first, so stress at A. Our bending moment is 40 kilonewton meters. You could leave it in kilonewtons and get kilopascals, or you can say 40 times 10 to the third, and you'll get pascals. Our C for this point, so that's from the centroid of the shape to the distance we're taking at, so there to there. That distance is 0.075 meters. And it's all over our moment of inertia, so 15.1042 times 10 to the negative 6th. That's going to give us 199 times 10 to the 6 pascals, which is just 199 megapascals. It also wants us to sketch on a volume element acting at each point. So all we're really doing is showing whether it's in compression or tension. So the moment is pushing up on top, and it's going to be pulling down on bottom, because that's where the arrow is. So we'll get that this piece, because it's above the centroid, is compressed. So we're going to have arrows going in. So now if we look at point B, our moment of inertia is the same, our bending moment is the same. Only thing that changes is our C value. So we're here now, so our C is only to that point, which is only going to be 0.025. So stress at C, we get 40 times 10 to the third, times C, which we said is 0.025, over the exact same moment of inertia, 15.1042 times 10 to the negative 6, gives us 66.2 megapascals, and that's above the centroid, so that's still in compression. So now if we look at point C, we say that's right there. So that's the same distance away as B is. That's still the 0.025. So the equation would be the same, or that should have been B. Stress at C will be the same equation. We'll still get 66.2 megapascals. Except now, because we're below the centroid, we'll have a volume element in tension instead of compression.